I took this class. This is like
after spring break, and I know you're all ready. You have written wonderful things for your midterm because this is part of your midterm lecture, and you are going to integrate things like
technology, cybersecurity,
technology, cybersecurity, and policy. So you're going to integrate those ideas, and the context today is going to involve radars and networks associated with radars. And so there are lots of formative questions in the assignment. And our speaker today is Frank Sanders. I keep doing that because I know Fred Sanders, who was at MIT in meteorology when I was there. And Frank Sanders is over at NTIA. He's going to tell us about technology, cybersecurity, and policy, focused in and around radar. So please, let's thank our speaker for today.
Thank you very much, Dr. Curry, for that kind introduction. First of all, can everybody hear me okay? Back row, you can hear? A little louder? Okay, good. Okay, right. That's what I like to check. All right.
The microphone is for recording. We're going to post your presentation on the website so the students will have that as well.
And by the way, it's great that you actually said Fred, because my wife and I have an inside joke we can tell you about later where she calls me Fred. So it's actually perfect. All right. So again, I'm honored to be here today, and what we're going to talk about is ultimately how we have done some testing at the ITS laboratory, Institute for Telecommunications Sciences, which is part of the U.S. Department of Commerce, which manages U.S. government radio spectrum. And by way of a very brief introduction, and I need to ask people to kind of indicate with a show of hands what they know. Regarding radio spectrum, first of all, everybody's familiar with radio spectrum, right? Good, all right. In the United States, are people familiar with the FCC, the Federal Communications Commission? Good, yeah, people know the FCC. Pretty much everyone's probably heard of that. How many people have ever heard of the National Telecommunications and Information Administration, NTIA? Oh, well, actually, that's pretty good. Actually, that's great. So, briefly, NTIA, which is the agency that I work for, is the federal spectrum manager, and NTIA does for federal government radios what the FCC does for private sector radios. So if the U.S. Army, the Navy, Department of Justice, Interior, whatever, needs to operate a radio system, that gets regulated through NTIA. And NTIA has an office in Washington, D.C., and they have a laboratory where I work here in Boulder, Colorado. So, given that NTIA does spectrum management, we're going to talk today about some spectrum sharing. People are familiar with radio spectrum bands, correct? That there are bands for television broadcasting, there are bands for police and fire department radios, and so forth. There are also bands for a lot of other services, including radar systems, which we're going to talk more about later. It used to be, years ago, that when people wanted to use a radio band for a new purpose, the existing users in the band were moved out of that band and they would be moved into a different band. And that came to an end a few years ago when a lot of available spectrum turned out not to be really available anymore. So, the way that we get new users into the spectrum in the United States today is not usually to actually move people out of a band, but rather to hold some kind of an auction, which is conducted typically by the FCC, and the auction proceeds, the money that companies pay to get to use new spectrum, is no longer used. It used to be used to buy out the previous user and move them to a new band. But nowadays, instead of buying someone out of their condo, what we're doing when people buy the right to use spectrum at an auction is we don't move them out. We keep the existing users in the band. And the person who bought the Spectrum says, okay, so I just spent $35 billion for what exactly? The answer is you spent $35 billion, and that's the kind of money it goes for sometimes, for the right to share the spectrum with the existing users. So to go to an analogy with a condo, you buy the right to share a Spectrum condo. You get to move into the condo and put your stuff in a bedroom, but then it turns out that the existing condo occupants don't leave. They stay where they are, and if they want to use the bathroom, the living room, the kitchen, they get to use it whenever they want, and you can't. You get to use the bathroom, the living room, and the kitchen whenever they happen to not be there. And that's spectrum sharing. And what we're going to talk about today is news sharing at 3.5 gigahertz, and specifically 3,550 to 3,650 megahertz, so 3550 to 3650. So, as I said, we've got the condo analogy here where the new radio spectrum users have to only use spectrum when the existing users are not using it. That means that the new users have to have a way to tell when the kitchen, the bathroom, the living room are in fact in use or not in use. And with radio systems, that means that the new users have to detect when the first users, we call them the incumbents, the first users who have all the rights, who get to keep operating the way they've always operated and not be hindered, the new users have to detect when the incumbents are using radio frequencies, and the new users have to avoid using those frequencies themselves whenever the incumbents are using the spectrum. And again, this is the trend in spectrum management in the United States because it became hard years ago to find new spectrum to just move the old occupants of the radio band out and move them into another band. It used to be they would push them up to a higher frequency and let the new people come to lower frequency, but again, we just don't really have that luxury now. So, a couple of years ago, the FCC came up with an idea for doing spectrum sharing at 3.5 gigahertz. Again, that's the frequency range. And who was occupying the condo? Who was the existing user of that radio band? Radar systems. And the radar systems are not entirely, but for our purposes today, we'll say mostly, nearly entirely, radars on Navy ships, U.S. Navy ships. We'll talk a little bit more about those, but the radars specifically are on aircraft carriers, and these are on both the really big angle deck carriers that have a big angle deck sticking out the side, and also on smaller so-called attack carriers. These radars are used for air traffic control. So the aircraft carriers themselves are ships that are nothing more or less than airports that move across the ocean. And what does an airport have to have? Air traffic control. When you're going to enter the pattern, leave the pattern, land, take off, you've got controllers who are controlling. They have to know where the planes are. And the way that they do that is with what's called a primary radar and a secondary radar. And the FCC said, okay, we want to put in new communication systems, and they're probably going to be more or less long-term evolution, LTE type systems, although it doesn't have to be LTE. But the assumption is that it's probably going to mostly be LTE. We're going to move new users in who are going to be running LTE, and the LTE networks using this spectrum will be deployed on shore. And the Navy radars are on aircraft carriers at sea. And again, they're going to share. And the radars are the original users, they're the incumbents, so they're supposed to be able to operate unhindered, unimpeded by the new shore-based systems, and they are not supposed to basically know that the shore-based systems are even there, if this all works out. Now, here's a photograph of the radar. It's called the SPN 43. The Navy people call it a SPIN 43. S stands for shipborne. P stands for radar, because in World War II, when radar was developed, R was already being used in an acronym for radio. So they took the leg off the R and they said P will be radar. Or maybe it's a Cyrillic R, a Greek or Cyrillic R that looks like a P. In any event, and so it's a shipborne radar, N for navigation. It's used for navigation purposes, specifically for air traffic control. and it's the 43rd unit in the series. These radars were originally designed and built in the 1960s, 1965, 1968, and I like to tell people that if I were trapped on a desert island with 6 other people and I had to build a radar out of coconuts, this is the radar I would build. If I were teaching a radar lab, this is the radar I would use because it's a very solid but basic radar. It just follows air traffic. It's not fancy. The way it works is there's a big parabolic, semi-parabolic reflector right here. This reflector produces a beam, a radio beam, that travels out in space in this direction. Echoes from aircraft in the sky bounce back into this reflector. The time delay between when a pulse is transmitted and when an echo is received is used to determine the range to the aircraft, which they always call the target. It's not military target, it's just target. In the radar world, everything is a target. And the direction of the target, the aircraft, is determined by the direction of the antenna. If the antenna was facing this way when the radar pulse echo came back, then we know that the aircraft is that way, and so forth as it spins. So it sends out a lot of pulses. It transmits pulses at 1 billion watts, effective isotropic radiated power, EIRP. Is everybody familiar with EIRP? Okay, good. So the transmitter is a megawatt. The antenna is 30 dB of gain, which is a factor of 1,000. So 1,000 times a megawatt is a gigawatt. 1 billion watts of effective power coming back out. We'll talk more about that in a minute. This thing spins. By the way, it's on a roll-stabilized gimbaled mount at the top of a ship's mast. This mast is about 50 meters, about 150 feet above the water. That's where these 2 sailors are working. The ship rolls, pitches, and yaws like this. Up, so the pitching motion is like this, the roll is like this, the yaw is like this, and all that 3 degrees of motion goes on with this thing spinning, and so this big gimbal up here stabilizes it. This is a counterweight on the back to just balance it out front to back, fore and aft. I've been around these antennas, I've been on these antennas. If it was running and you were up here, it would squish you like a bug. It is immensely powerful. It spins at the rate of 1 revolution every 4 seconds. And one other thing to note, and this is true for airport radars that you'll see like at DIA or anywhere else, on top of the main radar reflector, and you should know this if you're in telecom, is another antenna that looks kind of low profile, like, yeah, there's another antenna up there. What's that? Anyone know what that is? Okay, that is what a lot of air traffic control is actually done with. That's called a beacon, and it's a side note for today, but I'm just going to note that here's how it works. The beacon antenna transmits coded pulses at 1,030 megahertz. This is a worldwide standard for all aircraft all around the world at all times and places. And this is called an interrogation antenna. It sends out interrogation pulses, they're coded, and as the radar rotates, it just goes interrogate, 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 constantly. And if there's nothing out there, the interrogation goes into space and is never heard from again. But if there is an aircraft out there with a beacon transponder on board, which is designed to pick up the 1030 pulses, 1030 megahertz pulses, then that transponder on board the aircraft sends a coded response back that says, "Hi, I'm here." And when the air traffic controllers acquire this on an aircraft carrier, an airport or whatever, they'll say something like Cessna 7642 Golf, squawk 7725 and ident. The pilot dials in 7725 and hits ident. There are only 3 bits. This dates to the 1940s, World War II. And now on the air traffic control screens downstairs in the bowels of the ship, they see this beacon interrogation with a response back from the aircraft that says 7725. They know that that's that particular airplane because they told the airplane to transmit that code. This also gets range based on time delay between interrogation and response. It also gets azimuth based on where it was pointed when the interrogation and response occurred. But it has a third piece of data that's good to have. It records, actually a third and fourth piece, it records, as I said, the aircraft identification, which this will not give you. This just shows a blob on a screen, which we'll look at in a minute. It also reads the altitude of the aircraft from the altimeter in the aircraft cockpit. So it says the aircraft is at 5,322 feet according to the aircraft's own altimeter. This radar does not do that. This radar has a very broad vertical beam, so it doesn't tell you the altitude, but the beacon does. Between the two of these, you do air traffic control because this allows you to see anybody who doesn't have a beacon, has a beacon disabled, or whatever might be going on. But this one gives the third dimension of altitude and the fourth dimension of identification. So just kind of a side note, but be aware of that. We're talking, though, about the sharing with the primary radar, the big antenna. So we say we're going to do this sharing. Well, what's the catch? I already said that radars are the highest powered transmitters there are. A typical radar transmits 1 billion watts of effective radiated power into space. Why do they have to transmit so much? Because the signal that a radar transmits flies out of the antenna and drops off as 1 over r squared until it hits the target out here in space, boing, and then the target is a point source, and the target echoes back that energy, which still drops off again at 1 over r squared. So if you drop off at 1 over r squared out, and then 1 over r squared coming back in, what's the total rate of drop off with distance? R to the 4th. Holy cow. That is a killer. And it is such a killer that even if you're transmitting 1 billion watts out from a typical aircraft at a typical distance from the radar, and if I were teaching a class, we'd go through all the details, you're going to get 1/100th of a trillionth of a watt. 10 to the minus 14 watts is what's coming back into the receiver. That's what you're going to detect on. So, and this comes into the spectrum sharing side, if interference, like from one of those shore-based radios, gets into the radar receiver, it turns out, and we'll talk about this later in talk, at 1/4 of that power level, which is 1/4 of 100th of a trillionth, which is 1/400th of a trillionth of a watt, then that radar target, the airplane, can just drop off the screen. Now, how do we know that? And we've had people who did not believe us. 10 or 15 years ago, we had people who were saying, who wanted to do the spectrum sharing, who said, that can't be right. That cannot be right. We said, okay, fine. We can do modeling, theory, analysis, and simulation, but we also do measurements. And so to do these measurements, we've got ITS engineers, including me, who go out to radar sites. We also have engineers. We have a guy named Bob H.S., for example, who do the simulation and modeling. And we check the modeling and simulation of interference into radar receivers by doing actual measurements with radar receivers. And this is the important part, under controlled conditions. Meaning we do not, for example, just radiate a signal into a radar. That is not a good controlled condition because we cannot control propagation factors, so we're not going to worry about that. So, to do measurements on effects of interference in radar receivers, we hook up a radar to our own target generator. It's a thing that we build ourselves, which makes fake airplanes for the radar that we inject into the radar receiver. And to the radar receiver, those fakes look like the real thing. It's a series of little pulses that looks like a real radar. And then in addition to that, we inject interference into the radar in a controlled way, and we vary the interference power against the targets. The target power is, by the way, is adjusted to give us a 90% chance of detection with no interference. You never get 100% probability of detection. That does not happen. You can get 90, 95, 99. We set it to 90. There are reasons for that. And then we inject interference at various power levels and watch the fake airplanes disappear as we do it. And we did that for this Navy radar. So this is a picture of the Navy radar. And this is at a shore station where the Navy does work on these radars. As I said, this thing dates to the 1960s. The receiver was updated from vacuum tubes to solid-state technology in the 1980s. So it has had some updates, but still. And that megawatt of transmitter power that is turned into a gigawatt of power when it goes out of that high-gain antenna, that magnetron is right there. And the actual magnetron tube is about that big. And the reason that they like to use magnetron tubes and say vacuum tubes, Yes, is you can get 1,000,000 watts of power out of a tube this big. You cannot do that with solid state technology. Solid state technology that would get that power out would occupy a set of racks, equipment racks that would be about this big to get that same power out. So tubes are excellent choices if you need to get a lot of power out, which you do because of that 1 over r to the 4th and that difficulty in detection. What we did here, and by the way, here's another view of the room. Yes, it's a top-of-the-line working space. What we did was we pulled this rack out. This rack contains receiver electronics, and we coupled our interference and our fake airplanes into this rack, and we sat over here and watched this radar display and looked at the targets that we generated disappear and reappear as we changed the interference power level. So here's one of our engineers, a colleague of mine, who's literally hooking into the radar. We have little clips, and we clip in there. We calibrate the system to verify that we have 90% probability of detection on the pulses that represent the airplane. We also calibrate the interference power levels. And then we turn on our interference generator over here. This generates a signal that looks like, in this particular case, looks like LTE. So as far as the radar is concerned, it's an LTE signal, and it's coming into the receiver along with the desired targets. And we're going to look to see what happens when we do that. So here's a picture of what happens when we do that. We have 10 desired targets that we're generating artificially, quote fake, but to the radar they look completely real. And those 10 targets are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see that, well, that's not like totally clean. No, it's not. It's a real radar. And this is a raw radar display. So you've got these 10 targets, and we adjust their power, and then we count 200 rotations of the radar. And someone, either me or someone like me, actually sits at the radar like this, and every time it comes around, every 4 seconds says 10, 10, 9. We do that and we adjust the power level until out of 200 rotations, we've got a 90% probability of detection. And then we turn on interference. LTE interference on the radar frequency, the interference to noise ratio, which is the interference power of the LTE signal relative to the internal receiver noise power of the radar. The radar has a receiver that has a temperature, and that temperature generates internal noise. By the way, side note, so in a room like this, which is, we'll just call it room temperature, what is the amount of thermal energy generated by everything in the room in the radio part of the spectrum? How much thermal energy? All of our bodies, the walls, the carpet, everything in here is generating thermal energy because the electrons are moving around and they're moving at room temperature. That thermal energy is minus 174 decibels relative to a milliwatt per hertz of bandwidth, minus 174 dBm. That's given by Boltzmann's constant multiplied by the temperature of the room, absolute temperature multiplied by your bandwidth, so minus 174 dBm. But the radar receiver generates its own noise even on top of that. So we adjust the interference to be, in this case, minus 9 dB, meaning 9 dB below the radar's internal noise. And this is where people said, you're not going to see anything. I mean, it's 9 dB. If it was 10 dB below, what would be the linear factor that it is below the noise? If you're minus 10, this thing is minus 10 dB relative to something else, in absolute terms, what's the offset? Factor of 10, because a decibel is 10 times the log base 10 of a power ratio under all circumstances. So at minus 9 dB, the interference power is about 1/10. It's just a shade, just a hair, a bit above 1/10 of the noise inside the radar receiver. And then we inject the interference at minus 6. Minus 6 dB is 1/4 of the noise level of the radar receiver. Then minus 3 is half the power of the radar receiver internal noise. So we're still below the radar internal noise with our interference. And you would think sort of naively, well, that couldn't cause interference, it's below the noise level. And then finally, we go to 0 dB. At 0 dB, the interference power level is equal to the noise level of the radar receiver. Well, watch what happens. First of all, see this wedge? Ignore it. That has nothing to do with anything. That is an artifact of the fact that this cathode ray display has a beam that spins around like that, and when you take an exposure of the screen, you get that cursor over here just spinning and moving around. So that has nothing to do with anything. That's an artifact of taking the photograph. Keep your eye on the targets. Here's the targets. Now, you might notice if you really squint, and I've had people give me a hard time on this, that you can see just a tiny little flicker of a hint of a little something underlying those 10 targets. But you can't really see it. And in fact, when we do our measurements, we find that does not cause any problems for radar target detection. But when we hit -6, where the power coming in is 1/4, the interference power is 1/4 of the power level of the radar internal noise, look, you can still kind of pick out targets. There's one, there's one, there's one, there's one, and kind of one, and so forth. But down here, and this is just random chance, it's blurry. So we count another 200 rotations, and we get the probability of detection on 200 more rotations at -6. And then we go to -3. Well, at -3, look, I mean, it's pretty much of a wipeout. And at 0, it is a wipeout. By the way, how could that be? If the radar noise power in the receiver is up here, and the interference power is down here, below it, how can this cause interference with seeing radar pulses, which are coming up a little bit up out of the radar noise? By the way, the pulses from the fake targets, they're about 1 dB above the noise, about 1 dB. The reason is that noise power adds. This power here adds 1/10 to the radar internal noise power. This power here adds 1/4. This power here, 0, doubles, right? Because if you have this level of radar internal interference, internal noise, and this level of interference, and the two add up, you double it. So that's why you see this fairly devastating effect. So to go back to it, what we end up coming up with is a criterion that says that you need to keep the interference power level down 6 dB below the radar's internal noise, meaning it needs to stay at 1/4 of the radar internal noise, or you'll start to lose targets. You'll begin to lose aircraft. You don't lose all the aircraft all at once, but you can see, I mean, it's starting to impact. So, moving on. So, in order for the spectrum sharing scheme to work, and it was the FCC's scheme, you have to know when there's a radar offshore, and the radars will not tell you where they are, and the Navy will not tell you where they are. The Navy is adamant that they will never intentionally or consciously reveal any information about where a ship is at sea. They just don't. You can take the harbor cruise at San Diego or Norfolk and see what's in port, but they will not tell you what's out at sea. So, the idea to sharing is that we have to have shore-based monitoring sensors that look for the radars on the Navy ships offshore, those aircraft carrier radars offshore. They look for the radar signals, and when a sensor sees a radar signal coming from a ship hitting it, then that sensor has to measure the power level of that radar signal. And it then has to send an alert if that power level from the radar exceeds a certain threshold. And we're going to go through that a little more in a minute, so I'm not going to stay on that right now. But the sensors, just some terminology, are called, I don't like this, but it's what they gave us, Environmental Sensing Capability ESC receivers. It's a fancy term for monitoring. It does monitoring. They're built to look, these are monitors that are built to look for radar pulses. And when one of those ESC monitors on shore sees a radar at a critical power level, we'll talk more about that later, then the ESC talks to an onshore network controller for LTE, and it says, hey, network controller for LTE called the Spectrum Access System, the SAS, hey, I'm seeing a radar signal exceeding a certain power level, you need to do something, and we'll talk about that in a minute. But briefly, the SAS then tells the local base station transmitter that's in the area, get off the frequency or turn off entirely, because if you keep going any longer, that radar is going to come in close enough that's going to cause interference to the radar receiver. Now, the Navy did not want me to put in a picture of an aircraft carrier, so I said, fine, I will put in a picture of this, but this is not an aircraft carrier. Anyway, it doesn't matter. So here's your Navy ship offshore, and it's sending signals out in all directions in space all the time, and some of those signals hit one of these ESC monitoring stations onshore. And somewhere near that is a base station transmitter that they call a CBSD, stands for Citizens Broadband Service Device, I think. It's just a base station transmitter for an LTE phone. It's the same as what you're talking to with your phones right now, except it's at 3.5 gigahertz. And we have to do a calculation to know that if this much signal, however this much is, we'll talk more about that, but if a certain amount of signal coming from the radar hits this station, then what's going to be happening, and nobody can do this directly with the radar receiver because there's nobody inside the ship monitoring the radar receiver for interference power, then based on a mathematical calculation, that's the key, a mathematical calculation, we calculate that a certain amount of power coming from that base station hitting the radar receiver is going to hit this critical power level of -6 where they start to lose targets. So you start to see this is a little complicated. There's one thing that simplifies the math, and it's this. We assume that the propagation term, the loss, L sub P, propagation loss, L sub P, going out from the radar to the monitoring station is equal to the propagation loss from the shore-based station that could be causing interference back into the radar receiver. And that makes that propagation loss drop out of all the equations. Why do we care? Other than it makes it simpler. Here's why we care. All of this is solid engineering technology except for when people start to argue about radio propagation. People who want to share a spectrum will say that radio propagation is lousy and that no interference will happen because the propagation loss is super high. People who don't want to share the spectrum, who are the incumbents, say, no, 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 no. Propagation losses are low, low, low. We're going to get a lot of interference power. And this is where people start arguing. And this is not a technical problem. This becomes a people problem. And they negotiate, and they go back and forth on 90%, 10%, 50%, this, that, and the other thing. But as long as that propagation term drops out of the math, it doesn't matter. It's gone. However bad or good the propagation is from the radar to the monitoring station, we assume it's just as bad or good coming from the interfering source back to the radar, and it drops out. So this is from an NTIE report, and there will be a quiz later. So no, I'm not. But it's on the material. Okay. So if I were teaching this as an actual multi-class session or something, we would go through all this, but we're not right now. So here's another diagram that shows how this sharing works. There's a ship offshore, and its signals are being monitored by these monitoring stations onshore, A, B, C, D, E, F. There's going to be a network of these stations running up and down the U.S. East Coast, the Gulf Coast, the Pacific Coast, the Alaska coast in places, Hawaii, and other places. They're going to have to build out, they being industry, working with FCC, will build out a network of these stations, these environmental sensing capability stations, and it's kind of like something that dates from Roman times. Just a side note, when the island of Britain was occupied by the Roman Empire back about 2,000 years ago, there were persistent problems with pirates, raiders, who would sail across the North Sea from what's now Denmark, Norway, parts of Germany, and they were called Saxons, and they would land on the British coastline, and they would raid inland settlements, and then they would run away. And the Romans built a network of monitoring stations very similar to this ESC network. They had people in the monitoring stations who watched for activity offshore. If they saw activity offshore, they raised an alarm by lighting a signal fire at the top of the tower. They had a network where they could operate semaphores from one station to the next to say that basically this station sees ships offshore that don't look good. And then the Romans would deploy cavalry from a fort somewhere in the area to come down to the vicinity of that station that was doing the sensing. This is a very similar concept, very similar to the old Saxon shore. And it was called the Saxon shore, not because they liked them, but because the Saxons kept invading the shoreline. They were pesky. So I want to take just about 5 minutes to act out about how this would work. I need 6 volunteers. 6 volunteers. I'm not asking, actually. Come on, 6 people. It's easy. Okay, you, come on, keep going. Okay, I guess I'll have to pick some. Okay, there's 3. You, please. 4. You didn't volunteer, so how about you with the glasses here? 5. Sure, thanks. Do I have a number 6? Anyone else? Okay, number 6, come on down. We're going to act this out. I'm going to act this out briefly so you see how this works. All right, so you're going to be the radar transmitter, and radars put out pulsed emissions and they spin in space, and they're a gigawatt. So the radar works like this. I don't want to blind anybody. You can all see that it's flashing. Okay, so what you need to do is you're going to, well, technically you would do this. Technically you would rotate like this once every 4 seconds. I'm not going to ask you to do that, but I will ask you to scan it back and forth.
Do you want me to move this while I'm doing it?
Yeah, if you can, yeah. Okay, radar receiver. You're going to be the radar receiver. The radar receiver gets no flashlight because the radar receiver transmits nothing, and yet she is the linchpin of this whole situation because she must be protected from interference, even though she transmits nothing. And the only way that we know where the radar is by looking at this signal coming out of the transmitter. What's generating the interference? What's generating the interference is a CBSD, cellular base station node, which is this. It's about 5 watts. So I'll ask you to step over here and just kind of stand here, there you go, and radiate toward the radar receiver. And by the way, one thing, you two have to stay close at all times because you're physically locked together in the ship. All right, mobile phone. You are going to come over here and you're going to sit down here because you're low to the ground and you get no flashlight because you're not transmitting enough power to make any difference. So I'm sorry, but you're worthless. Nevertheless, all right. All right. Now, finally, we're going to set up one of the monitoring stations. This will be you. And you will be over here close to the CBSD base station. Kind of like within a kilometer or two, maybe. Okay, so good, that's good. And then finally is the spectrum access system. This is the decision maker for the system. So, spectrum access system, you're going to stand about here. All right, now, so if we didn't have the receiver paired with the transmitter, and you walk toward me, receiver, just come on over toward me, you would come in close enough that you would eventually get blinded by that little light. That would hit that -6 IOVERN level, and you'd be starting to lose targets, lose aircraft. We have a problem in the air traffic control pattern. But, go back, but luckily you're paired with the transmitter. And the transmitter, move it a little bit because the beam scans through space. But scan the beam a little bit over the monitoring station. Yeah, here we go, yeah, a little bit. There you go. You hit, boom, see that? You hit the ESC. When you hit the ESC at a particular power level that we calculated, would correspond to the power level where this dim bulb over here, the light, not you, is interfering with the receiver. Then what happens next is you say to the SAS, I've detected a radar at -89 dBm per megahertz.
I've detected a radar at -9.
89 dBm per megahertz, because that's a computed number. And then you, SAS, you go to the base station and you say, base station, turn off.
Hey, base station, turn off.
And that's how it works. Okay, that's good, thanks. All right. Thank you. Okay. Yeah, just a twisty. There you go. Thanks. Thanks very much. All right. So that's how it works. The reason I like to go through that is I've had cases where people flash pictures up and they say things, and I can tell no one in the room, including me, knows what's going on. So, all right. So, a tricky part about all this was that although this works for this current radar, the air traffic control radar, the Navy's going to build new radars in this band in the future, and the Navy would not tell us anything about those radar pulses, waveforms, or anything else. So we needed to, and we're going to get to this in a minute or two, we needed to test those radar detectors. We needed to test the ESCs that were being held up to make sure they detect radar pulses, but the Navy would not tell us what the pulses would look like. They said, that's classified information. So what we did was we used physics to look at what the radars would need to do. How big a target do they have to see, at what distance, and da-da-da-da-da-da. And we worked out a range of pulse parameters for pulse width, pulse repetition rate, and so forth. And we said, we think that if we test radar detectors within this range of radar pulse width, radar pulse repetition rate, and so forth, that we should be covering the range of all of your future radars for what they might send out as pulses. And the Navy reviewed our results. They said that your results cover the space of the possible waveforms, that is the pulse repetition rates, pulse width, et cetera, for the future radars, and they thought we were smart, but really we just applied physics. Which is, you know, when you merely know what you're doing, people think you're a genius or something. So we then worked with the FCC, the US Navy, and a group called the Wireless Innovation Network Forum, WIN Forum, which is an industry group, to formalize ways to test these radar detectors. We wrote a pair of NTIE reports and we published them to say, here's how we're going to test those ESCs. Because the ESC is the linchpin of this entire system. Everything depends on the ESC. And by publishing the procedures, we basically locked the procedures in for both government and industry and for the future, because other people in the future are going to want to build these things, and we wanted to lock all that in. And we signed agreements with the FCC and industry to do the performance testing on these radar detectors at ITS. So in the fall of last year, we had 3 companies that came in with radar detectors to get their new detectors at 3.5 gigahertz tested to see how well do they detect radar pulses. How well do they do? And the Navy and the SSC wanted a very high standard of detection. They wanted us to transmit 2,000 pulses of different sorts and types into these detectors, and the detectors were not to miss a single pulse type. So we did the testing through the end of 2018. We got the testing done by November, Thanksgiving of 2018. We had final reports drafted in December. There was the government shutdown that delayed things by about a month, but we still got these reports released by March, by last month. And so mercifully, I'm not going to take you through this whole thing, but this is the system that we built at the lab over here in Boulder to generate those radar pulses. We had a lot of different kinds of pulses that had to do a lot of different things, but we built that up to do that. And we then had that set of pulses from this rack of equipment here, that's that rack of equipment seen from an angle. That rack of equipment fed its pulses into a radar detector. This is one of the industry radar detectors right here. That's an ESC station. That would normally be mounted in the field on a pole, maybe 30 meters, maybe 100 meters, whatever, above the ground. And we played our radar pulse injection out on a big screen here so that the people from the company who were having their device tested could see what we were injecting into their detector, and then their detector output was on this big screen so we could see how the detector was responding. So everybody in the room could see what everybody else was doing. Nothing being hidden. Everything's up front, and we walked through a couple thousand pulse waveforms, and we would transmit the pulses in, and then we would look to see if the detector detected, and if it did, it was noted. And we had a nice little automated system for doing all this, and that all worked well. And so, having completed that testing, and we did end up getting successful certification results for all the detectors that were brought in 2018. We then gave the test result reports to our sponsors, our industry sponsors, and they in turn have fed those reports to the FCC, and the FCC shares reports with the Navy, and this will lead in the near future, like in the next 6 months, we'll say, probably 6 months, to initial deployment of those sensors on shore. There are certain terms and conditions the FCC is going to impose. I don't want to, bear through too much of that right now. But basically, this work to test those radar detectors, which again are the key to making this whole system work, as you saw. The whole trick is that when that radar got a certain amount of energy into that detector said, I'm at minus 89 dBm per megahertz. That's just the number that we worked out from the math. It talks to the SAS. The SAS says, oh, okay. If the SAS turns over, sends a message to this transmitter and says, transmitter, 3.5 gigahertz transmitter on this frequency, get off the air. By the way, it can either terminate all transmissions or it can just change its frequency. But it's got to do one of them. It's got to do something to get off that frequency. So we're going to continue to apply this work in the future as the Navy deploys new radars in this spectrum, and as new industry companies who want to use the spectrum, again, on the sharing basis. You understand, again, that, see, they can't use the spectrum when there's a ship near the shore. They can only use it when there are no ships in the area, obviously. This will be applied in the future for new entrants into the spectrum onshore and as the Navy deploys new radars in the spectrum. So, we're about on time. I like to do that. So that concludes the talk, and I appreciate your attention and would like to ask, does anyone have comments, questions? I can't imagine there couldn't be a single question.
So first, let's thank our speaker. And let me pose something. Oh yes, that's all fine, but
I hate that word, but. No, it's good.
no. We're never going to be on ships. There are no real applications for radars anywhere in the normal environment of people who are studying network engineering. So why do we care about this?
Because, yes, why do you care? Here's why. Because when I talk about new spectrum which is getting shared, and I don't have an NTIA spectrum wall chart here with me, but if I did, I would show you that enormous amounts of radio spectrum are currently used almost, not entirely, but nearly exclusively by radars, which means that when people who are building and using communication systems that work with networks, for example, and not limited to, LTE systems, LTE communication systems say, I want to get into some new spectrum. More often than not, the new spectrum they want to get into, which they think they can share with, is radar spectrum, mainly because radars have a lot of spectrum. By the way, why do radars have a lot of spectrum? Because, for one thing, they don't share well because they have those sensitive receivers. They share well with each other, it turns out. We could go through that. I'm not going to go through it now. But they don't share well with communication type systems. You saw how, an I over N level of -6 causes interference. So when communication system engineers are looking to get into spectrum, they will more often than not, be looking to get into radar spectrum. And so, just for example, these are some communication engineers from a major company, really major company, who came in from California with their radar detector, and they don't know anything about the radars they're trying to share with. We told them generally what kind of radar pulses they have to detect, but they literally say, I don't know, which is to their misfortune, because then I take them into a conference room next door and I say, you're going to get the Frank Sanders 1-hour class on radar because I need you to know the basics on how this works. So we go through that. They learn some of the basics and they say, oh, that's why they transmit so much power. That's why they're so sensitive to interference and so forth. So it is a good idea, if not a requirement, for people who are building and designing and deploying new telecom systems to know about radars, because the new telecom systems are typically, very often, going to be sharing spectrum with radars. And if you're going to share spectrum with radars, your problem is not so much interference from the radar into your receiver. And by the way, you might say, well, why? You said the radar transmits a gigawatt of power. Yes, it does. But that gigawatt is transmitted in pulses that are 1 microsecond long, that are typically spaced at a spacing of 1 millisecond apart. So a microsecond is what fraction of a millisecond? 1 microsecond to 1 millisecond is 1,000. So the pulse only occupies time for 1,000th of the total interval between pulses. So even though it's a high power pulse, if it hits an LTE receiver, like basically if it hits your phone or the base station you're talking to, it probably won't actually interfere with it. The LTE system will essentially try to retransmit some data packets and push through it. It's the radar that has the problem. So you need to understand that if you're sharing with the radars, you've got this extreme sensitivity situation for the radar receivers. And because you're the new entrant, you're the one who has to share the condo when the current users aren't using it. You're the one who has to use the spectrum when the radar isn't there. You need to know how this works.
Thank you.
Yes, back here.
So on a kind of more nefarious thought,
Yeah.
could you potentially transmit 3.5 gigahertz off the coast and knock out radars like that?
Yes, if you wanted to do it, and I have commented on this, you wouldn't even have to go off the coast. All you'd have to do is sit near one of the radar detector stations and transmit pulses that are about a microsecond long, spaced about a millisecond apart, with an antenna that's just pointed up toward the base station. And you just and you could knock them off the air. We don't imagine that there's anyone who is that nefarious who's going to do it, but ... But yeah, you could, because, I mean, that's just how it is.
In that same vein, then, that if you keep the LTE system online by doing exactly that, you could just totally wipe out radar around the coast?
Oh, yeah, if you keep those kinds of signals on, if the LTE continues to run and transmit, yes, you would cause interference to the radars. So what's your name and address? No. No. But yeah, you could. Yeah, you could. This, yeah. Yeah, there is an assumption built into all of this that the people involved, who are large industry companies, not that corporations can't do bad things, will be good actors. If they're not good actors, we'll eventually catch up to them. Now, they wouldn't catch up to them quickly. The people who would be chasing them would probably be me and some people at the motorway. But, so there is an assumption here that the people involved, the companies involved will be good actors and not bad actors. We do anticipate that there will be technical problems, but we don't anticipate that people will intentionally try to break the rules just to benefit themselves. Well, here's the thing. If you do that, I'll tell you this, you will eventually get caught, and when you get caught, it's not going to be a pretty situation. So best not to. Anyway, yeah. But a good question. Good question, though, yeah. Anything else? Yes, Professor.
Okay, so you've talked about the boundaries. You've talked about radars on ships. But the majority of the spectrum inside the nation is, it sounds like it would be fine.
Good question or comment. And yes, that is true. Most of the continental United States is clear of these radars because they are not in the continental interior. They're
no ships.
Right. So for the most part, the companies will be able to operate with pretty much no impedance inside the continental U.S., although there is a statistic that I like to cite in connection with this. And this is based on some census data that I plowed through years ago that NOAA, National Oceanic and Atmospheric Administration, published. And it was in response to a question that I had in my head. And the question was, where do most Americans actually live relative to shorelines and coastlines? How evenly distributed is the American population? According to NOAA census data from a few years ago, over 50%, like 51, 52% of all people who live in the 48 continental United States, we'll put the two freak states of Alaska and Hawaii to the side for the moment, no offense to anyone from those states. In the lower 48, a little more than half of all Americans lives within 50 miles of a shoreline. So a little over half of all Americans live within 50 miles of either the Atlantic Ocean, the Gulf of Mexico, or the Pacific Ocean, which means that the rest of the continental United States is inhabited by a little less than half of all Americans. So in a sort of density plot, the interior of North America is sort of not inhabited much. Yeah, you're in a city like anything, my God, there's a lot of people around here. But drive out into eastern Colorado, if you've never done it, you should. Go out to the Pawnee Buttes National Grassland, and you'll see what the rest of things look like. Like, wow, there's nobody out here. In fact, it's becoming gradually depopulated. Lack of job opportunities and da-da-da-da. So where the carriers want to install their stuff is in the middle of the continental United States. It's true. Denver, Salt Lake City, and so on and so forth. But their biggest market, over half of all Americans who they want to serve, are on the shorelines within 50 miles of the coast, which is where the Navy radars sail through. So it is a little bit out of proportion to what you might think it is. But you're absolutely correct, Professor. If we had, or to the extent that we do want to deploy these systems inside the continental U.S., which we do, they can deploy like in Denver, no problem. There are no Navy radars in Denver. Oh, they got to be careful, and there aren't. But you got to be careful because sometimes there are shore-based stations that are in weirdly unlikely locations. Yeah.
I just wanted to follow up with what you just said. Is it economically viable then to install these 3.5 gigahertz when you have 2.5 and 5 already?
I'm an electronics engineer, not an economist, but the people who work as economists for these companies and for the SEC say it is economically viable. And I'm not questioning that, but I will say that time will tell. And really, I'm not questioning it, but you know, we will find out the hard way, if you will, empirically. Over here.
So I was just wondering, the spectrum sharing capability, I mean, in this process, it requires the Navy to disclose all the operating frequencies. I mean,
Oh yeah, good.
involved,
Yeah, Navy operating frequencies. So,
it could compromise their capabilities.
yeah. So some radars are not classified in terms of their emission characteristics, and this radar that I showed you is one of them. You can look this radar up in reference books, and the gain of the antenna, the transmitter power, the pulse characteristics are public domain knowledge. And so someone who wants to do engineering with this type of radar that we're talking about here can do it pretty easily. There are radar systems that do have classified frequencies, classified operational bands, classified antenna parameters, pulse parameters, etc. I'm going to say, and this is not me talking for NTIA or the US government, this is me personally talking, it's a little silly in the sense that anyone who sits at a distance from one of these things can in fact record the signals and look at them if they want to, and they are gigawatt transmitters, so they're not subtle. So you could identify the characteristics of various radars if you wanted to. Now, it would be a little trickier to identify what the ship was associated with it, because a ship that's even 10 or 20 kilometers offshore is not really visible from shore. But long story short is, so some of the radars have open literature, information, and that's easy. Other radars are closed, classified, and we could have gotten a briefing, had we wanted it, we could have gotten a briefing from the Navy on these future radars that have these classified parameters. We said, oh no, 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 please don't. Because as long as I've never been briefed, I can come up with those waveforms and say, I think your waveforms are going to fit within this range of pulse widths, this range of pulse repetition rates, so forth. And all the Navy had to do was say, yes. And so, since I have no classified information, I can't accidentally screw up and give it to anybody anywhere, and I can do all my work in the open and nobody interferes with me on that, which is what I like. So, yeah, again, a good question. I think we're out of time.
Okay, so let's again thank our speaker. And of course, on behalf